in literature. Yeah, one more common assumption in literature, but the important thing is we need to be able to verify independence with data because yeah, otherwise we'll be really gambling and at the risk of losing all the validity of our results. So yeah, so there's a classical problem and has been carefully studied in many classical studies and many classical models, right? But the question nowadays is that when we receive data, we don't really have often we don't have a model to begin with. We don't have any information about joint distribution. So our question here is that under this completely distribution-free non-parametric setup, can we still distinguish independence from independence? Yeah, non-parametric, right? And turns out this is not a simple problem. And we'll begin with a consideration of a very simple case, dependence between two variables, two continuous variables, and we suppose we have NIID observations. And we'll consider this so-called copular setting for which the marginal distributions are uniform over 0, 1. We can achieve this copular if we know the marginal distribution, marginal CDF, then we can use the CDF transformation. If we don't know it, we can use empirical CDF and work with ranks, right? But the idea to consider this copular is to single out the problem of the joint distribution. Right, here's a long list of a small proportion of literature on this topic. You can see people have been publishing papers since 1940 on this problem, and people are still working on papers around test of independence. So you may wonder why people have to work so hard and publish so many papers on the same topic. And one reason behind that is under this distribution-free non-parametric setting, dependence is something that can go really well. I'm borrowing this picture from this paper showing that the form of relationship can be nonlinear, non-smooth, non-continuous, and even sometimes even non-functional. And to illustrate how difficult the problem can be, I'm giving my audience a little quiz. So I have here 2 plots of 50 points. And in one of the 2 plots, A and X and Y has a relationship. In the other plot, X and Y are independent. So the question is whether you can distinguish the two, right? So let's just do a show of hand over Zoom. If you think plot A is showing some form of relationship between X and Y, please raise your hand. Nobody. So I guess yeah, So I guess all you choose B. But yeah, the answer is A, right? The 4 points in are related because the points, all the points in A are sampled uniformly from these grid lines, right? But the point of this quiz is that because the grid line is very dense, so if these grid lines are hidden, the pattern is not so apparent. Yeah, so and this is this grid lines. I gave it a name. I call that bisection expanding cross. You can regard this thing as a fractal because it has a hierarchical structure. So in the first level, what you have is a cross in this unit square. To reach the second level, you take the 4 midpoints here and you expand bisector until they intersect. And you can repeat the same process to take the midpoint, expand bisector to get level 3, level 4, and so on and so forth. And there are 2 interesting properties about the uniform distribution over these grid lines. The first property is that if you look at things marginally, the marginal distribution are uniform 0, 1, so it's a copular, right? But if you look at things jointly, then the joint distribution is degenerate, right? All points are on the line, so also support is one-dimensional, right? So in that, so these 2 properties will lead to an interesting paradox. That is whether we should describe the uniform distribution over the grid lines as a strongly non-independent or nearly independent. So the distribution appear to be strongly non-independent because at every level D, it's a degenerate, right? And if you check the total variation distance from the uniform distribution of the grid lines over compare that distance to the uniform distribution over a square, which means independence. That total variation distance is 1, the maximum possible value. So in that sense, this distribution is kind of strongly non-independent. But it also appears to be strongly nearly independent, right? In a sense that the grid lines are getting denser and denser, and if you fix any point xy in this unit square, and you let d go to infinity, and then you realize this joint probability is converging to the product of x and y, which is precisely the product of a marginal probabilities. So in that sense, it's nearly independent. So yeah, my question for you again. Yeah, if whether you would like to describe this the distribution as a strongly independent or nearly independent. If you prefer to describe it as a strongly independent distribution, please raise your hand in Zoom. Okay, so I guess you prefer to describe it as nearly independent, but actually both are correct. There's no contradiction, and I will show you why in a later slide. Yeah, but not only this is a mental kind of a quiz, it's also a challenge to existing methods. So I have this shocking simulation showing that for d equals 4, this fractal distribution here, many types of independence are powerless, even when the sample size is raised to 20,000. And this experiment was shocking because we only have two variables, right? We only have two variables, and we have 20,000 observations. It's like we can plot everything out, and we can see the relationship with our eyes. But many tests are saying no, we cannot detect it. So why is that, right? There are many reasons, but one important reason is this non-uniform consistency. So the theorem basically says that if you want to test independence versus straight away from independence in total variance distance, then for any test you can think about, there exists an alternative distribution, a form of relationship such that the test you're thinking about is powerless. So the intuition behind this theorem is quite simple. It can be simply explained by this fractal. The idea is that you can consider any good test, any test that is universally consistent, meaning for any fixed alternative, for any fixed form of relationship, as long as your sample size is going to infinity, you are guaranteed to have a asymptotic power of 1. So this property is called universal consistency. So it's a good test. But in reality, remember, we never have infinite amount of samples. We always work with a finite n, right? And once we fix our sample size n there, you can keep expanding this cross. You keep expanding this cross until d is really large, that uniform distribution over these grid lines are so close to the uniform distribution over the fractal over the square, which means independence, that the test you are thinking about becomes powerless. Right, and this result is it's not for total variation distance alone. So there's a group from Samworth with Samworth group showing that this is similar result also holds for other distance, L2 distance, I think, in this paper. But yeah, if you look at this results, the results from message from these results are quite negative. Basically, they are saying we should not expect one single test to be able to uniformly detect all forms of relationships, not even all levels of this fractal, right, which is far away from independence in some sense. Yeah, so in practice, this means blind spots. This basically says every test has a blind spot. Yeah, so what to do, right? So yeah, so the question puzzled me for a while, but then I came up with one solution. That is, yeah, so if one test is not good enough, I'm going to construct a sequential test. And if testing exact independence is not possible, I'm going to test approximate independence. And this approximation of independence and the construction of sequence of tests is through a filtration approach. The filtration is constructed from a classical probability result of a binary expansion. So that, remember, we are now in a coupler setting. Everything is within the unit square, and the marginal distribution are uniform 0, 1. And for uniform 0, 1 variables, there's a classical result in 1950 showing that they can be decomposed into this sum of A's and B's, which are Bernoulli halves, IID Bernoulli halves. In principle, you can regard them as bits, right? Writing things into binary system instead of decimal. So this is the idea of binary expansion, and you can truncate this expansion at any finite depth d, right, to get this UD and VD. And once you do this truncation, you see that UD and VD are nothing but discrete uniform variables over dyadic fractions, right? And also very easy to see that as d going to infinity, UD converts to U in probability, and VD converts to V in probability. But these marginal convergence results do imply a joint convergence in probability. And that's important because that means we can approximate, right? Let's just say we can approximate any relationships in U and V through that in UD and VD, right? And this consideration of approximation is apparent if you look at everything as a filtration. That is, at every level D, what you learn 1A and you learn 1B, and as D goes to infinity, you learn everything, right? So that's a filtration idea. But why is this a filtration idea helpful? To see that, I'm bringing this famous quote from George Box. All models are wrong, but some are useful. The idea is that when we write down UD and VD, we know upfront we're working with the wrong model, right? UD, VD is not UV. So clearly we're working with the wrong model. But turns out this wrong model can be quite useful in many ways. The first thing it brings out is a universality. That is, although the relationship between U and V can be arbitrarily complicated, as long as my D is large, we can always expect a good approximation from UD and VD. The approximation error is exponentially small. The second thing it brings out is identifiability. Remember, the problem is hard because things can go wild. We kind of lose control. Things are not trackable. This is because we don't have distribution, we don't have parameter, we don't have likelihood, we don't have anything, right? But on the other hand, if we do this binary expansion approximation and then at every finite depth level D, what we have is a 2D by 2D contingency table, which is a well-defined model with a well-defined parameters, well-defined likelihood, and well-defined everything. So as a consequence, we can achieve the desired uniformity. That is, we can be uniformly consistent at every level D against any alternative that's direct away from independence in total variance distance. Remember, this is not possible if we don't do this approximation. So because of these advantages, what I'm proposing to do here is to consider statistics that are functions of A's and B's. I call them binary expansion statistics, and the framework to test approximate independence in UD and VD, I call that binary expansion testing. Yeah, this is my bet on independence. Right. All right, some remarks before we move on. First, I constructed the filtration as if I know the marginal distributions. But even if we don't know the marginal distributions, we can work with the ranks and the empirical CDF and construct the filtration. And the theory and the methods are shown to be similar. Yeah, the second remark I want to make is that the binary expansion filtration is certainly not the only way to approximate a coupler, through a filtration approach. However, there are several advantages of this approach through binary expansion. Yeah, so the first property is about simplicity of the sigma field, right? The sigma field generated by binary variables, the sigma field of UD and VD is generated by finitely many binary variables. If you are thinking about the other bases such as cosine and sines, then the sigma field can be arbitrarily complicated, right? And the second point is also related to simplicity. There's a binary variable has this nice property that the relationship between is linear. So which means they are uncorrelated if and only if they are independent, right? And that's good for us because that means for us a second moment is good enough, right? So this linearity is helping us. The third perk here is that the binary expansion is by decomposing a distribution into bits. What we can is a related thing or methods to bitwise algorithm, right? By constructions, statistics that are functions of A's and B's that can allow bitwise operations to process the data, and that will lead to fast computing. So because of these advantages, what I will propose to do is to take this binary expansion filtration to study dependence. Although coupler theory is well developed, we're not aware of a similar approach. Yep. So now let's take a look at what we can do with this filtration. So if we take this binary expansion approximation and truncate and at a finite depth C, then the problem of test independence becomes testing discrete uniformity versus a delta away from discrete uniform distribution, right? And this is a classical problem in the continuity table, and the likelihood is something we all know, the multinomial likelihood, right? So for this classical problem with this classical likelihood, there are many classical tests, such as chi-square tests, that are uniformly consistent. But why shouldn't we use the chi-square test? Right, for mainly two reasons. So first, the degree of freedom of chi-square test is 2 to the power d minus 1 squared. It's growing exponentially, and it's going to eventually hurt the power. The second thing, drawback of chi-square test is about interpretability. It's for practical purposes, right? So the idea here is that the chi-square test can give you a very small p-value, and you can, based on the small p-value, you can claim x and y are related to each other. But this small p-value from chi-square test cannot tell you how the two variables are related to each other, right? So the interpretability is not so clear. And what we are proposing to do is to improve upon these aspects by through this binary expansion approach. What we propose to do is to consider grouping the cells in the continuity table together through interactions of a binary variable in the filtration. I'm going to skip many theorems here, but essentially this consideration of interaction among binary variables will lead to a reparameterization of the multinomial likelihood on the previous slide. And I'm going to illustrate that with the 50 samples on the previous slide with d equals 2. So for 2 bits from A and 2 bits from Y. 2 bits from U and 2 bits from V. So the idea is that now we have a 4x4 contingency table if you look at the first 2 bits. Yeah, so sigma field is generated by 16 variables, 16 binary variables. Yeah, one of them is really trivial, it's a constant. But the other 15 non-trivial binary variable, each of them will divide the unit square into half area in white and half area in blue, right? The new parameters, so-called interaction odds ratios, are defined as the ratio of the product of white cell probabilities and the product of blue cell probabilities. So why are these new parameters helpful, right? So the idea is that if you look at the classical parameterization with cell probabilities, cell probability carries both the joint distribution information and the marginal distribution information. But turns out we can separate them through this interaction odds ratios, this new parameterization. The idea is that if you look at the marginal, so-called marginal interaction odds ratios relating to, involving only A's or only B's, then contrasting the white region to blue region is providing you information about the marginal distribution, right? These binary variables. However, if you look at those so-called cross interaction odds ratios involving both A's and B's, then contrasting the white region to the blue region is providing you some information about the joint distribution, the relationship between X and Y, right? And indeed, yeah, so we have a theorem showing that all the information about dependence is summarized in this cross interaction odds ratios, and UD and VD are independent if and only if this cross interaction odds ratios are ones. They're white and blues are balanced. So in a sense, these cross interaction odds ratios are two contingency tables, just as correlations are two multivariate normal variables. If we want to study dependence relationship between variables, then we should focus on these parameters. Right. Perk here is that the sufficient statistics for these parameters are simple. They are so-called these symmetry statistics, basically checking the difference between the number of points in white region and the number of points in blue region. Right. Just take the difference between white points and blue points. So yeah, we should construct statistics that are as a function of these sufficient statistics, these symmetry statistics. And the first test we propose is quite simple. It's we call that MaxBet. The idea is that for each of these cross interactions, we count how many points are in white, how many points are in blue, right? And we look for the biggest discrepancy, which happens here for this example. There are 50 points, and we have 32 in white, 18 in blue, right? And yeah, so then we can use the binomial p-value to get get a p-value for this particular configuration of white and blue. Because we have considered 9 configurations due to the different interactions of A's and B's, we'll multiply that small p-value by 9 to get overall max bet p-value. Right? So it's a quite simple procedure. Just count white and blue, and then use binomial and then Bonferroni correction, right? Yep. Yeah, but it's a simple procedure, but turns out this can be optimal, right? So this theorem shows in the minimax of this procedure. That is, as long as the sample size is growing at this rate, then the power of max bet can be arbitrarily close to 1. But if the sample size grows any smaller, if you change this big O to small O, then no test can be uniformly consistent, meaning for any test, you can think about there's an alternative distribution such that the type 2 error is at least something positive, right? So in that sense, this is optimal rate, and the max bet already attains this optimal rate under these two, given these two simple conditions. Some remarks here are that consistent of chi-square test requires a big O for 2 power T samples, and if you compare the rate here, you see max bet can be more powerful in these cases. And I would like to talk about the conditions to reach this result. So it's a very mild condition. First condition is basically the alternative, the statement alternative. Second condition is comparing the maximal signal in our infinity norm to the overall length, right? So the L2 signal. So this is checking how spiky the signal is, right, in this alternative distribution. And so if a signal is spiky, then using maximum is better, right? So that's intuition. And those conditions can also be regarded as sparsity constraint because it can be satisfied when the signal is about square root sparse. Yeah. So, but yeah, and this sparsity consideration has already also considered in the Annals study by other people. People have shown that if the signal is square root sparse, using maximum is better than using chi-square test. So that's about the power, and also about this optimal rate. Basically, this is useful in a sense that it tells us how many bits to consider when you have a certain amount of sample, right? If so, basically say this rate basically say d is growing at grow at most log 2, and so if you have 128 samples, you don't want to see more than 7 bits, right? So that's about the power. Another thing I want to mention is about the interpretability, right? We mentioned that existing method they are very not one drawback for practical reasons is that they are not very interpretable. But here, when the math rejects independence, when we reject null hypothesis, we also know the formal relationship because the test will return with 50% of area, either white or blue, with significant more points. Right, so that's providing some information about global dependency, and yeah, so I would like to illustrate that with the fractal again. So the idea is that all these fractals, if are falling into the white regions of these interactions, right? So all points are, if you sample points over these grid lines, they are all in the white region. So p-value for this test at this depth is here. So 2 to the power n here because all n points are in the denominator in the white region, and yeah, so this is the number of cross interactions, and this 2 here is for two-sided test, white and blue. So very simple p-value, right? And if you apply that to the 50 points in the quiz, you see, yes, it's generated with d equals 5. If you test at d equals 6, then p-value is yes, this value, very small p-value, right? Because 2 to 50 is in the denominator. And this p-value also explains the paradox I mentioned earlier. The idea is that for this the example in the quiz, the grid lines here, the first 5 bits are really independent of each other. U5 and V5 are really independent. So in that sense, U and V are nearly independent. Basically saying if there's any relationship between U and V, the relationship is hiding in the remainder term in the binary expansion filtration, right? So in that sense, it's nearly independent. On the other hand, if you want to test whether U and V are independent, you really want to test that, you go down one more level, you look at one more bit, and you get this very small p-value. And this small p-value tells you that U and V are strongly non-independent. So there's no contradiction here, right? It's just depending on at which resolution you will prefer to look at this distribution, right? So yeah, that's about interpretation. I want to make a comment about the connection to computing. So how the computer works, right? They work with bits, right? And bits are basically the A's and B's in this binary expansion, right? Yeah, so one message I want to mention is that bits we all use them all the time for computing, but bits are data as well, right? We can construct statistics with bits, and we can make inference with bits. If you look at the bat at the depth d, it's nothing but testing whether data are independent up to the first bit. That's exactly what we are doing, right? And the bits are free, right? Yeah, as long as we process that data, with a computer device, I think most people will do that nowadays. Then bits are already stored in the little machines, right? Yeah, so if we construct statistics that are functions of A's and B's, what we can do is to consider bitwise operators and directly operate over the bits, and which will lead to fast computing, right? You can work with true and false and all kinds of gates. And indeed, we have a software written by my student, Zhang, that's 100 times faster than distance correlation, which is a very popular method in practice. Yeah, so now let's take a look at some numerical studies. So first, power studies here is these plots have to look good, right? But we did compare our method with many others under many settings, and yeah, BAT here is showing robust performance because of min-maxity, right? We are protected from the worst case. Yeah, but more interesting is application to explorer data analysis, EDA, right? So the idea is that when we're graduate students, one thing we often do for a small data set is to make a scatter plot matrix for every 2 variables. Make a scatter plot, use our eyes to identify anything interesting, right? So this for small data sets. For large data sets, this is much more difficult because too many the scatter plot to look at. right? So what do the people do in practice, right? So this is a true story from a large lab in genetics. We are working with the gene expression, so the number of variables is in the magnitude of 10,000. So what they do for the EDA is for every pair of gene expression, they use a distant correlation, test independence, their independence using distant correlation, so they get a p-value, right? So they get 10,000 choose 2 is about 50 million, right? So they got 50 million p-values, and they sort them from the smallest to the largest. So this step is good, right? Distant correlation is a good method. Sorting p-value is certainly a good idea. So this first step is good, but the problem comes from the second step. Second step doesn't look so great, right? Second step basically what people there can do is to hire some few graduate students to read this 20,000 plots one after another. And you can see that the problem, this is certainly not the best way to use the time of our talented students, right? But you can also see the source of the problem. The source of the problem is interpretability, right? We know things are related to each other, but we don't know how they are related. So that's why we have to hire graduate students to read these plots one after another, right? But what I want to say is BET can help here. BET can help you with interpretability, speed, and also about time. Also power, right? So I would like to illustrate that with a real-time experiment, and by calling it a real-time, I'm going to simulate the data, do the experiment right here, right in front of you. And so what we are going to do here is to simulate a data set with 256 observations, 100 variables. The first 10 variables are 5 pair of binomial normal, so you know it's a linear relationship. But from variable 11 to variable 100, I'm going to randomly pick 2 variables, and I'm going to randomly assign one of the 3 nonlinear relationships, parabolic, circular, or sine, to these 2 variables. And the goal of the experiment is to use the BET to identify which 2 variables are nonlinearly dependent and what their nonlinear relationship is, right? So that's about the experiment. And to ensure reproducibility and fairness, and also for fun, I'm going to ask you to suggest random seed to begin the simulation. But before doing that, I would like to make a note, again, comparison with distant correlation. Distant correlation is not suitable for this task because it cannot distinguish linear relationship and nonlinear ones. So it's not suitable for this task. And also, on the other issue is that distant correlation is a little bit slow, right? So it's scanning over this 100, all the 5,000 pairs over this 100 variables is going to take distant correlation about 3 minutes. So these are the 2 practical drawbacks of to use distant correlation. And we can compare them, keep them in mind, and compare them when we're doing the simulation. So here's the R code, right? So nothing fancy, but yes, this is R code to generate the data, and I need a random seed to begin the simulation. Can I have any suggestion from the audience? Any numbers? Any number?
How about 42?
42, great. The answer is 42. Right, so let's put this R code in the RGUI, nothing fancy, right? So data generated, and you can see the data is here, generated today at 12:01 p.m., right? So you know this is a fresh made data, and you know I didn't cheat, right? This is another presentation, I guess. Oh, thanks. Late to the later. Yeah. So this is fresh made data, right? If you open this spreadsheet, we see this is nothing. This is what we work with every day, right? We have data matrix with 256 rows, 100 columns. The first 10 columns, I know that 5 pair linear relationship, so not very fancy. But from variable the 11th column to the last column, there are 2 columns hiding here with a nonlinear form of relationship, right? And I guess it's not easy to see, right? Not so easy to see. But now we do have I asked my undergraduate student to write a GUI for this test, so people don't have to code, right? And it's quite simple, just about the buttons of clicks. And there is ready to go. Again, the first thing we would like to compare is the speed, right? The existing method takes about 3 minutes to finish the process to do the 5,000 tests. And we can compare the bitwise operations here. We can count the time together, right? So it's like 1 second. I think it's already done. It's just saving the data. So in 2 or 3 seconds, it's already done. Now how to detect this nonlinear form of relationship? The idea is that the linear relationship can be captured by the interaction of a first bit. You can see a kind of monotone relationship here. So if you simply uncheck this one and click plot, here we go. This is the saying we have this variable 35 and variable 75. We have more points in the white region, and from from this this plot we can see that this is kind of parabolic type of relationship, right? But it's always a good idea to double check. So let's go back to the code. We have recorded which two variables are related and what their relationship is, and let's check. 35 and 75, and it's indeed parabolic, right? So it works here. Yeah, hope it's clear. It works here. It's fast and it can detect nonlinear relationship. So in 3 seconds it can scan over to 5,000 times and identify this one pair of nonlinear relationship. And I think it's safe to say here that up to this point, I'm still not aware of any other method that can do the same task at the same speed. I know deep learning doesn't work here. So I hope this method can help our students save for some of their time on more interesting things. All right, and we did apply this same method to our code, right, to real data, right? So this is the TCGA breast cancer data where there are indeed 10,000 genes, right? And 50 million pair. If we were to use a decent correlation, it could take us 30,000 minutes, but for us it's about 300. So we're much faster. Out of the 50 million, we identified 160,000 nonlinear relationships, most of which are not known before. These three plots are showing one pair of genes here, these two genes. There are more points in the white region, so nonlinear relationship. So the question is, what's driving this nonlinear relationship? The idea is there's a basal subtype of breast cancer marked with red triangles here and here. So the idea is that patients with this subtype of cancer, the gene expressions of these two genes are quite different from the rest of the population. So if the data collection is a mixture of subtypes, this mixture of distribution here will create this nonlinear form of relationship, and we can capture this nonlinear relationship, and we can draw. We can then track back to see what's driving this relationship. And the interesting biological fact is that both of these two genes have already been individually confirmed to be highly related to basal subtype of breast cancer. But back then there was no research on their joint behavior to this breast cancer yet. So this EDA is suggesting we should do that kind of study. The joint relationship to the cancer, basal subtype cancer, because you can just draw a line here and classify this subtype cancer with 90% accuracy. But if we're only used to use one of the two variables, the accuracy is in the 70s, right? So we can gain a lot by using things jointly. So that's one thing we can gain from EDA. So this is summarize my first part. So we only assume only IID observation of continuous variables. We achieve uniform consistency and optimal power, clear interpretability, and efficient computation. So here's my first paper. Here are some follow-up paper on multivariate extensions, and also applications. So our package is freely available on CRAN. So that's my first part. I would like to pause here for a few seconds if to take some questions.
Hi, Kai. I wanted to ask, could you describe the relationship to the multiscale Fisher independence test by Gorski and Ma?
So it's connected to this has to which the other test? Sorry.
The multiscale Fisher independence test.
Oh, multi-fit. Right. Yeah. So it's related. So the idea is they are also consider all kinds of partitioning and scanning, right? And here we are doing more like a global formal relationship, and multi-fit is good at capturing local form of relationship. Right? So that's the main difference. Yeah. But we don't both use partitions. Yeah.
Thank you.
Yeah,
there's no other question right now. It's been very clear.
Okay, great, thanks. Okay, let me move on to the second part. I actually think the second part is more interesting. I have about 20 minutes to go. So okay, good. So so the second part is to answer the question that now that we can detect some form of relationship, how can we make use of it, right? So when we detect a correlation, can we build a linear model and make use of the correlation, right? But what if we can detect something nonlinear? What can we do with that? So Yeah. So yeah, my collaborators, Benjamin Brown, my great student here, and Xiaolin Meng at Harvard University. Yeah, so it's again, it's about non-parametric modeling of relationships. So before talking about nonlinear, complicated things, let's begin with a linear formal relationship. So yeah, begin with something we all know, linear relationship between binomial and normal, right? So binomial is a linear in the sense that they are independent if and only if they are uncorrelated, right? Yeah, in this case, we can write the conditional expectation of y given x as a linear function, right? So we know this very well. But yeah, just a few slides ago, I mentioned that binary variables is also linear, right? For any binary variable a and b, they're independent if and only if they're uncorrelated. So the first question we asked is, yeah, can we write this conditional expectation of b given a as a linear function of a, right? And we began with again simplest case, two Rademacher variables, for which the marginal distribution are taking value plus minus 1 with equal probability, right? Expectation is 0. And then two facts, if you consider this a and b, then two facts are immediate. First, a squared is 1, right? This is a no-brainer, right? Because a is taking value of plus minus 1. But second fact is maybe not so apparent, right? No matter how a and b are related to each other, if you multiply them together, the product is independent of a. Yeah, it can be easily checked by taking covariance, right? So if you check covariance, a squared is 1, so you have EAB and EB and EA here, they are both zeros, right? So the two simple facts, and we can combine these two facts together to study expectation of b given a, right? The idea is if this is our target, right? We can always insert a squared there, right? A squared is 1, right? So we can insert that, and then we can rewrite this product as ab times a, right? And then we use the second fact, ab and a are independent. But then we can factor out this expectation, right? Expectation of AB times A, right? And so that's yeah, so that's a function of A. And if you look at things carefully, you realize this is just a linear model, right? And yeah, it's a linear model with a 0 intercept, and the slope here is precisely expectation of AB, right? And what's more interesting is the error term, the residual, and yeah, the residual is turns out to be AB, the product of AB. Yeah, if you look at this, right, this AB is independent of the predictor, and this AB is explaining the remaining variance in the response, right? So there's a complete parallel to the Gaussian linear model in our textbook, right? So we were a little bit surprised by that. And then our next question is, Rademacher is too peculiar example, right? Whether this result is general, right? And the answer is yes. And that is the theorem of binary expansion linear effect or belief, right? So the theorem basically asserts that conditional expectation of b given if you have b one binary response and the p binary predictors, then the conditional expectation is taking a linear form, and the coefficients in this linear form is nothing but our old friend least squares, right? Yeah, so there's a general result, and we were a little bit surprised here because when I was teaching first year graduate courses, I teach students when you have a binary response, you fit a logistic regression, you fit a probability regression, you fit something GLM, but don't do least squares. And I was wrong, right? I was wrong because the story is not completed yet, right? Yeah, it turns out if a predictor themselves are binary, then the optimal thing to do is to do least squares, right? This is minimizing this mean squared error, right? So we're a little bit surprised by that. And then our next question is, well, this is so simple expression. Do people know that already? We checked in the literature. So yeah, indeed, there are a lot of closely related things. So in statistics, the earlier reference is a Bahadur representation model in 1960s. In signal processing, there's a Walsh transform wavelets, right? And in econometrics, there's people study a linear probability model. So they are all related to this, but none of them were taking this least square type of approach. So we decided to study this more carefully, and turns out there are a lot of new insights when we take this representation. Yeah, so yeah, binary dependence between binary variables is linear, right? So what if things are not binary? Yeah, we can do binary expansion, right? We can decompose things into bits, and then we can fit all these linear work with all these linear models, right? Yeah, so yeah, the first paper basically what we did is basically we redid the linear model theory, but not with the Gaussian variable, but with the binary, right? So turns out there are some shared property between binary and the Gaussian, and there are some unique ones. So this table summarizes them. So for both independence equivalent to Gantt correlation, for both conditional independence is linear, and for both slope are zero related to conditional independence, for both least square is also MLE. Right, but some unique feature is that one thing is that the residual story doesn't quite generalize to in the binary case. Yeah, so this is open problem number one. Actually, I want to pause here. I mentioned that we really have a more question than solution at this stage, and this paper, I hope that I can be an invitation for all of you to help us to develop this direction. Yeah, so this is open problem number one. We don't know what we mean by remaining variance, right? How to export to learn there. The other thing, yeah, but the unique feature about binary is that the slopes are within a compact convex set. So this is facilitates kind of regularization, right? And yeah, so I would like to talk about. I have a few minutes left. Regularization and yeah, how to use this belief to study other form of relationships. So regularization is needed because you can see the belief theorem is actually mathematically trivial, right? It has a dimensionality issue that turns all the difficulty problems into this dimensionality. The idea is that if you yeah, so this we can consider linear form with this A tensor, which is Kronecker product of all these binary vectors, and yeah, so dimensionality of this A tensor is like 2 to the power p, right? But if you look at the we have p binary predictors, how many total states are there? Also 2 to the power p, right? So there's always a way to write any function of p binary variables into a linear form, right? Into this form, right? So in a sense, the belief here is saturated model, right? And yeah, so so belief and conditional expectation is a special linear function there. So the proof of the belief theorem and this lemma is really trivial. And it's a dimensionality problem. Dimensionality in this setup, it's certainly a challenge, right? But we don't regard it as a drawback of this framework because we are not, there's no free lunch. We are not really making the problem either, but we are not making the problem harder either, right? Because this the exponential growth of dimension is a faithful reflection of the complexity of problem to study relationships, right? Here, remember, here we are trying to study. We don't want to make any assumptions and want to study all kinds of relationships. So the problem is exponentially hard, right? It's getting exponentially harder if we include more variables. So yeah, this is a faithful reflection of problem, and we think belief is a unified general approach to study all these form of relationships, right? Having said that, this regularization is needed because 2 to the power p can easily exceed n, but the regularization is feasible. We can always shrink things to our 0, and regularization is meaningful in this is connecting sparsity in the linear model and sufficiency. So the idea is that if you consider the group generated by all the p predictors through with action being the multiplication, then they have 2 results here. First, if the linear model, if a belief is sparse, if slope is sparse, so sparse that the binary variables with a non-zero slope will form a subgroup of big group. Then conditionally subgroup B and A are independent. So that means all the relationship, all the relationship is summarized in this subgroup, right? There's a notion of sufficiency. The converse also is true. If we have sufficiency, then we must have sparsity. The coefficient outside this group must be zeros. Okay. There are 2 examples here, but I will skip them. Due to time consideration. And yeah. Now let's connect it with GLM and other things. So GLM, so what's a connection to GLM, right? It's also linear model. Turns out belief is a further generalization of GLM. So in a sense that all the GLM slopes can be regarded as a function of belief slopes. Right, so that's a generalization, and yeah, but this means GOM is imposing some model. The model condition lead to different interpretations, right? Particularly on interaction terms. We'll talk about this in 2 minutes later, and yeah, so yeah, that will lead to some issue in practice. Right, I want to mention. Another thing, drawback of GLM is complete separation, right? That's a well-known problem. Yeah, but for belief, there's no problem. It's just still least square and well-defined inference. Yeah, so another thing is the extension to continuous observation. So again, if I have U and V copular, right, and you want to how to study the relationship between U and V. Yeah, the idea you can decompose it into bits, and yeah, we have this theorem showing that the relationship between U, V, and U, the conditional expectation here is a martingale convergence double limit of these these conditional expectations, and yeah, so each of these conditional expectation is a linear model, right? And you can use belief here. And the whole theorem is shows this divide and concur type of approach to study any form of relationship. The idea is that there can be any relationship between U and V. We can decompose this nonlinear complicated relationship into many linear models, right, over bits, right? And for each linear model, we know the optimal way to estimate and to make inference of about parameters, and we can aggregate the information back to provide overall inference. And if you look at this carefully, the structure of this theorem is basically a neural network, right? U is our input and V is our output. And yeah, so the nodes here are basically A's and B's. And you can basically what we are doing here is regressing each nodes here, B here, over all the A's. And yeah, there's a linear aggregation to provide you overall inference about V. And yeah, so it turns out we don't need fancy activation functions or fancy optimization algorithms. We can just do least square over bits, and we have a mathematical guarantee, right? The martingale convergence theorem showing that we can approximate any form of relationship, right? So, but having said that, the regularization of this network, high dimensional network is certainly an open problem. There are a lot of things to do, and a lot of problems about related to selective inference when we are doing inference right here. So yeah, some numerical studies, classification result is robust. You know, this is again expected. But yeah, I would like to spend 2 minutes on this practical problem. So there's a long debate in political science. So about using the GLM. So in 1980, people say that when you are start trying to study interaction effect, you don't really need to insert the interaction term in the GLM because of compression effect of the nonlinear link function. I don't really like this concept of compression. I don't think it works, but people, you know, this is a seminal paper. People cited with 1,000 of citations. People are using it, right? Taking this approach. And yeah, of course, you know, a few years later, people argue back the compression-based interaction is an artifact, and we should always include interaction term and test its significance. Right, but then a few years later, you know, another group argue that compression is theoretically meaningful, and the interaction term is not always necessary. And you know, other group arguing back, you know, interaction term is always necessary. So you can see a lot of debates here, right? And you can see the source of problem, right? Because you know, people want to argue for their results, and this argument eventually becomes an argument about models, right? Because different models give different results, right? Interpretation of the models, right? So that will lead to all the kinds of this debates. Yeah, let's now see all the solution of all these debates through belief, right? So we're basically we did the analysis in this last paper, and the paper is about conflict between countries, which are binary outcome due to depend on 5 factors, 2 binary and 3 continuous. So what we did is to consider belief with 2 binary predictor and the first bit of 3 non-continuous predictors. And here's the result. All the 5 main effects are conformally significant. There are 6 two-way interactions being conformally significant. All other interactions not significant, right? One particular interesting interaction term here is the interaction between the first bit of capability ratio. This is a military capability, right? And the first bit of a smaller of 2 countries' polity score. This one variable is measuring the degree of dictatorship in the country. So this interaction means that if there are 2 countries with huge difference in military capability, and at least one of the 2 countries is under dictatorship, then bad things may happen, right? So this is a model that makes sense, right? But do we need to argue anything about this model? Do we need to debate with anyone? No, right? Because we are not assuming anything. We didn't assume any model. We didn't make any choice of link function. What we are providing are information, what data tell us up to the first bit, right? So this is useful inference without any model or any link function, right? So this is So this is how belief can be useful. So in summary, again, belief extract linear dependency, and there are new insights here. We can use that to understand GLM and neural network. It's regularizing that is necessary, feasible, and meaningful. But most importantly, there are many open problems, and we warmly invite you to help us develop this framework. And with that, I would like to conclude my talk. Thank you very much.
All right, thank you, Kai, for the great talk. So next we will have Hongjian Shi from Technical University of Munich to give us a short discussion. So Hongjian, please feel free to share your screen and start your discussion.
Can you see my slides now?
Yes, we can see it, but it's not full screen yet.
Okay, yeah.
Yeah, all good.
Okay. Thank you very much first for inviting me here, and I'm very honored to be the discuss of the Bet and Belief by Kai Zhang. I indeed got from the presentation, and first I want to start my discussion with a short summary. The takeaway I take from Zhang's presentation. The motivation to develop new methodology is first the non-uniform consistency. So no test can uniformly, in terms of the total variation from the independence, detect all forms of dependence, not even all the levels of the box example in particular. And so the goal of the first paper, Bad Independence on Independence, is to find a test that remains universally consistent and is also maybe nearly uniform consistent with respect to the total variation distance. Sorry for my typo here. So the highlights of the new approach BAT is first the uniformity. It enjoys the consistency at any depth against alternatives which are delta away from the independence in total variation distance. And the second highlight is the optimality. So the new method BAT enjoys the min-max property in the sample size requirement at any depth D. So the third highlight, I think, is easier interpretability. With the new method, we have a simple and clear interpretation of the dependence. Sometimes it is more important to interpret the dependence structure rather than just conduct the independence testing. And the last but not least is the idea of using binary expansion could lead to more general frameworks. For example, the binary expansion linear effect framework, as Zhang introduced in the second part of his presentation. Now I will have some comments and thoughts rather than questions. So first, the choice of the binary expansion seems like the most natural one. So has the author considered like other expansion instead of the binary one? And the second question about the choices of the tuning parameter, the depth D. So on page 17, it roughly suggests the D on the scale of log n might be the optimal choice of D. However, the box example on page 18 also suggests the depth required to detect dependence also relies on the dependent structure itself. So in addition, the powerful depth D is non-uniform in terms of total variation in this example. We notice all the total variation is equal to 1 in this example. So do the authors have any comments on this? And in addition, how do we choose the depth D in practice? And do the authors have any theoretical results for the in the scenario when we have the increase in D as the sample size and increase? The third comment is the idea of binary expansion can be generalized to higher dimensions when we want to test some independence between two random vectors x and y, when the x and y are no longer univariate. So where one encounters the curse of dimensionality, both theoretically and computationally. The last comment of Zhang's presentation is about the interpretability. So in practice, identifying a dependent structure, dependence pattern sometimes is more important than testing for independence. BAT can explain some functional dependence patterns as shown in the presentation, and also I also refer to the figure 5 of the paper. But what about like some more complicated ones when the dependent structure is no longer some functional ones, not the circle, not the sine function, but something like I show here, a uniform distribution over the unit ball, not the unit circle. So also this question also extends to the contents of the belief framework. What will be the benefits of leveraging neural network with belief in terms of interpretability? That's all my questions.
Yeah. Okay, I guess I can start. I guess.
Yeah, Kai, please feel free to answer those questions.
Yeah, thanks, Hongjian, for the great thoughts and the great discussion. Yeah, great questions. So let me answer your questions one after another. This is yeah. Could go to the previous slide. Yeah, perfect. Let's begin with the first the ternary expansion. Another ones. Yeah. So this is great. Binary expansion is certainly not a unique way. It's the best way to do it. There are other ways that can decompose the signal field and must have their advantages. For us, I think binary is the reason we choose binary is for two reasons. First, binary is connected computing-wise. It's connected to 0 and 1, the bits, right now it lead to fast computing. Thirdly, I'm not exactly sure about that, but also there's also important orthogonality idea in this binary expansion filtration, so that if you remember the white and blue regions, they can be regarded as orthogonal basis. So in a sense, the chi-square test we mentioned, we have a theorem showing that chi-square test is basically can be shown as the sum of squares of the difference of difference in white and blue regions, right? So it's a sum. So what we did is orthogonal decomposition of the chi-square test, and then the orthogonality means non-redundancy in terms of information, and we hope that could be useful in terms of improving the power. So yeah, so that's my I think that would be my response for your first question. We haven't considered others, but yeah, hopefully later we'll consider that. Second one about the choice of the great question. So yeah, so we are trying to the optimal detection boundary. We are working on that. I think the optimal detection boundary of any form of relationship should be a trade-off of few things. For example, for few things, first factor sample size n, second factor dimension p, third factor the strength of the signal delta, and the fourth, I think, complexity or the depth in the binary expansion, right? So the optimal detection boundary must be a trade-off between these few factors. Yeah, we know results for 2 dimensions, but for high dimensions we don't know. I think this trade-off and some results on optimal stopping will be the way to go in this theoretical type of direction. That this will be great solution. But in practice, it turns out, because in the past people mainly focus on linear kind of relationship. So d equals 2 can already provide a lot of useful inference. So right now, and the d equals 3, I revealing more, and yeah, with good power. So yeah, so we for practical purpose, I think 2 or 3 would be good. For increasing d, I think yeah, generally there's a trade-off between many things. We have to study that. Yeah, so that's the second question. Third question, when things are not no longer univariate, but we can still there's a certain dimensionality issue. Yeah, but we can take the same approach. And there's a paper. We have a paper. But beauty powered beast. In that paper, beauty is taking a characteristic function approach to decompose the all kinds of relationship into interactions of binary balls, and that works for any distribution in any dimension. So yeah, so that approach could be useful. Yeah. So, but having said that, yeah. So computation is certainly an important issue. This is still future work. So that's why we would like to invite all of you to help us. Yeah. And you have next question.
Yeah. So interpretability.
Right, interpretability. Yeah. So yeah. So interpretation is through the interaction of A's and B's. In the talk. So yeah, so and in general, it's not it can be a linear combination of it, right? Because again, the white and blue things are like orthogonal basis, right? So we can do linear combination of them, and you can to provide general kind of inference about the relationship, and this is all related to estimation of the joint density, right, through this basis. If you think about it, and yeah, so we are considering trees and other things. There are a lot of density estimation methods. I was connecting these two and these things into bits and to provide overall inference. And last question, neural network. Yeah, great question. Neural network. Our approach is more interpretable in a sense that the slopes can tell us the direction and strength of the relationship, right? So that's more interpretable here. And also using bits, we know it can be fast, right? So that's a good main benefit we think we can provide in terms of studying neural networks. Yeah.
Okay, thank you for your answers.
Thanks a lot again for the great talk and the discussion. So now I'm going to stop recording.